Let me begin today's lecture by discussing the assignment number 2. The problems are all given here. I will go through them one by one and give you some hints and ideas so that you can work them out yourselves. So, the question 1, you see I have this standard LPP. Remember, I refer to the standard LPP, which is minimization of C transpose X subject to Ax equal to B, X non-negative. So, for a standard LPP, you are given the 4 extreme points x1, x2, x3, x4, and the directions. There are 3 directions in the feasible set, d1, d2 and d3, and I have given you the values of the objective function at the 4 extreme points. So, the first one, C transpose x1 is 5, C transpose x2 is 7, C transpose x3 and C transpose x4 both have the value 4. The directions of along d1, there is no increase in the value of the objective function. C transpose d1 is 0. Similarly, C transpose d2 is also 0, but C transpose d3 is 4. Characterize all the optimal solutions of the LPP. So, I want you to, this information is enough for you to find out which is a optimal solution for your given LPP. Remember, the linear programming problem is a minimization problem. So, C transpose d3 equal to 4 does not bother us, because the value is positive here and it will increase in this direction. If I move in this direction, the value will increase with a multiple of 4, and my objective function is a minimization function. So, I chose this example particularly to show you that even though your feasible region is not bounded, because it has directions present in it, it does not disturb the minimum value of the objective function that we are considering here, because the direction that is present in the feasible region, the value of the objective function is increasing along that direction. So, therefore, now you can tell me what the minimum solution would be. Okay. Let us go on to the next one, number 2. Number 2, I am saying use a linear programming formulation to show that the constraints, I have given you 2 constraints with all non-negativity constraints on the variables, to imply that the third constraint will be satisfied. So, I would like you to think here, what do I really mean? See, if I want the third constraint to be satisfied, that means it should be greater than minus 18. What would you say that would be the value of the objective function? If you treat the left hand side, that is minus 6x4 plus 8x2 plus 7x3 minus 9x4 minus 5x5, if you treat this as the objective function, and if you want that the value must be greater than minus 18, you can now guess what should be the minimum maximum you have to guess. So, you can formulate this problem. That means you are trying to find out if this constraint, the last one, is implied by the first 2, which then you can formulate this as a linear programming problem, and then you can tell me that whatever your formulation, so whatever the answer of that linear programming problem is, final optimal solution value, then how will you, after having that optimal value, how would you answer this question? So, I want you to think about it. Okay. Now, problem 3, I have given you the optimal tableau for some linear programming problem. This is the right hand side, and you can see that the basic variables are x1 and x2. So, for them the top row Cj minus Zj's are all zeros, but you also have Cj minus Zj zeros for x3 and x4. So, therefore, I am asking you to compute alternate optimal solutions, because x3, for example, it can enter the basis and the value of the objective function will not change. So, if by bringing in x3 you have another basic feasible solution, that will also turn out to be an optimal solution. Okay, this is the idea behind. Yeah. Now, in problem 4, I have stated a linear programming problem, and I am asking, and find a basic feasible solution with the basic variables x1, x2 and x3. So, basically I want you to be familiar with the pivoting rules, and then work out the you want to bring x1, and of course in this order. So, x1 will be the first basic variable, x2 will be the second basic variable, and x4 will be the third basic variable. And once you do the pivotings, then at the end of this, when you get the table, you can check whether the optimality criteria is satisfied or not. If it is, then it is an optimal solution. Otherwise, you will say that no, this solution is not optimal. So, work out the fourth one. Okay. Now, yeah, fifth one. Yeah, let's just concentrate on fifth one. Yeah, so the fifth one, I have given you the starting tableau and I have given you the current tableau. And in this case, the problem I took from the book that writes the top row as Zj minus Cj. We have been using Cj minus Zj. So you just have to change the criteria. That means when I say that for a minimization problem, the optimality criteria requires that all Cj minus Zj should be non-negative. In this case, it will be that Zj minus Cj's are less than or equal to 0. So you can change the criteria, but the top row gives you the Zj minus Cj here, and you have all the information. Now, for example, I'll just give, so there are a lot of unknowns here, and I want you to obtain these. So the two tables give you enough information. Say, for example, in this case, your starting tableau, x4 and x5 are the basic variables. So in the current tableau, and in the current tableau, under the columns A4 and A5, you will have your basis inverse, right? And remember, your K and L would be CB B inverse minus CB B inverse. So write that down on one side on a sheet of paper. Then you can compute. Say, for example, here I am giving you that the value that here the Cj, I have not given you C1. C1 is an unknown right now, small a, but in the well, it is actually minus Ca, because this is Zj minus Cj. So starting thing, your Cb's are all zeros, therefore the top row actually is minus Cj, minus a is your C1. Now in the current tableau, this is 0. So you know the Cb B inverse. If you know the Cb B inverse, then you can compute the you can find out what a would be. So just remember what the formula I have given you and what should be the current values starting from this tableau. You can compute all the unknowns that I have asked you to compute. Yeah, for example, let me see if we can check some more. I can quickly give you yeah, say for example, under column 2 you have a C. So this is your A2, right? And in the current tableau, what you have is B inverse A2. So since you have B inverse already with you, the B inverse is given here 1 by 3 0, 1 by 3 1. So this times when you multiply it by C2, you should get 2 by 3 and 1. So you have the equation for finding out C. And this way, this will really help you to become very familiar with the pivoting rules and the working of the simplex algorithm. So that's the idea behind problem 5. Now problem 6, yes, this is I have taken from K.G. Murthy's book, and here the statement, okay, they don't write C transpose, doesn't matter, it's understood that C therefore is a row vector. So minimize your Zx equal to Cx subject to Ax equal to B, x greater than or equal to 0. So A is a matrix of order m by n, K is the set of, so here they are referring to the feasible region as K. We have been using the letter capital F. Fb is the minimum objective value in the problem as a function of the right hand side constant vector B. Let us just look at the, I'll just try to give you an idea how to look at these problems and how to go about answering them. Let me take up number 2. Number 2 says that the unboundedness criteria will never be satisfied while solving the phase 1 problem. Remember, when I was discussing phase 1 and phase 2 with you, I showed you that since you are minimizing the sum of the artificial variables and the variables are required to be non-negative, therefore the minimum value, the value of the objective function is bounded from below by 0. So there is no question of phase unboundedness criteria being ever satisfied in phase 1, right, because it is bounded from below, so it can never go to minus infinity. So the answer, so here when you answer question number 2, you will say that no, it will never be satisfied since the objective function value for phase 1 is bounded below by the quantity 0, by the number 0, right. Now look at number 4. If a tie occurs in the pivot row choice, during a pivot step while solving 1 by the simplex algorithm, the basic feasible solution obtained after this pivot step is degenerate. So tie means what? That when you take the minimum ratio is not unique. So you are having two different R's for which the ratio is the same. So therefore you have to decide which variable should leave the basis. Remember, in our case we said the minimum ratio occurs for xbr upon yrj, and we said we will choose that as, so xbr will leave the basis, and instead of that aj will the xj will become a basic variable, and the corresponding column will enter the basis. But if there is a tie, then I told you that there can be problems, there can be cycling, unless we determine, unless we make a choice in a unique way. And so I gave you Bland's rule. The Bland's rule said that you will decide on that variable, basic variable, to leave the basis which has the smaller index. So that means if you have a tie for 2 rows, then you will choose the row which corresponds to the basic variable with the smaller index. So that will be the rule, right? And of course that's what not being asked in question 4. It says that after this the pivot step will be degenerate. So obviously, because your theta value is the same for the 2 ratios, and so at the after pivoting, both xbr becomes 0, and suppose some xbs was also having the same ratio, that will also become 0. It will stay in the basis. You drive out only one basic variable from the basis, because you want to maintain the size as m, basis size as m. So if 2 basic variables are becoming 0, only one becomes non-basic, the other stays in the basis. So the solution will be degenerate whenever you have a tie in the minimum ratio rule. Okay, fine. Then we can go to problem 7. Yeah, 7. Let us read the problem carefully. Rank of A in 1 B M. Okay, full rank. If one has an optimum solution, there must exist an optimum basis. This I proved to you, right? Because I said that if there is any feasible solution, then there is a basic feasible solution, and we have also shown you that a basic feasible solution will always be an optimal solution. Okay, so that is that. Every basis consists of m column vectors, and a pivot step changes one column vector in a basis. Hence, starting from a feasible basis, the simplex algorithm finds an optimum basis in at most m pivot steps. In this question, they are asking you to comment. Do you agree with the statement? The statement is saying that you start with m basis vectors, so you have m columns there. Then you are replacing one column at a time, and you are improving, you are trying to improve the value of the objective function. So he says that once you have replaced, at each iteration you are replacing one basis column. So after you have replaced all the m columns, you should have reached the final solution, you should have reached the optimal solution. But we have seen in our own computations and so on that it is not true. It is possible that some column you replace, then it gets again replaced. So it is not necessary that once you change all the initial m columns in the basis, you will have an optimal solution. So this statement is certainly not right, right? And what combination and what order you have your basis columns, that matters, that gives you a different basic feasible solution. So you cannot say anything here. Okay. Then I thought that I will mention problem 9 here. Question 9 says if x bar and y bar are 2 adjacent basic feasible solutions of 1, the total number of variables that are positive in either x bar or y bar or both is at most m plus 1, right? Because x bar may be degenerate, so it has at most m positive variables. Y bar also has at most m positive variables, but remember they are adjacent, and I discussed it with you in the earlier lecture that the corresponding basis will differ in exactly one column. So that means the m positive variables in y bar, the m minus 1 are the same as the one in x bar, only one differs. So when you add up the total number of positive variables in x bar and y bar together, they will add up to at most m plus 1, because you may have degenerate basic feasible solutions, right? Okay. Then 17 and 18 and 19 I want to discuss. So let's put all of them together. Yeah. So now look at 17. The set of optimum solutions of any LP is always a bounded set. The set of, see, if you have optimum solutions, then the value of the objective function is finite, right? So obviously you will not have optimum solution on a direction, because if you are on a direction, you remain feasible that the value of the objective function keeps increasing. So this is what is being said here, that if you have a set of optimum solutions of any LP, then obviously it has to be a bounded set. Okay. And 18, if one has an optimum solution in which m plus 1 or more variables are positive, it must have an uncountable number of optimum solutions. See, now if you relate this to problem 9, see, what we are saying is that there is an optimum solution in which m plus 1 or more variables are positive. That means there are at least two basic feasible solutions which correspond to an optimal solution, which gives you the optimal solution, right? So if you have two basic feasible solutions giving you the optimal solution, then every point on the edge joining the two feasible solutions, optimum feasible solutions, will also be optimal. So you have infinite number of optimal solutions present. So if you have more than one, then you have infinite optimal solutions. I mentioned this also some time ago when we were talking about. Now question 19, if rank of A is m and 1 is non-degenerate. Yeah, I thought I should take up this because I want to introduce you to the definition that when is an LPP, when do we say that an LPP is non-degenerate? So that is when every basic feasible solution is non-degenerate. So this is possible in a lot of combinatorial optimization problem also. You have a situation where you know that any basic feasible solution will be non-degenerate. So that's what we say. Rank of A is m and 1 is non-degenerate. And every feasible solution in which exactly m variables are positive must be a basic feasible solution. So I would like you to think about it and answer the question. Okay. So this takes care of the assignment sheet. So I hope you enjoy doing the rest of the ones. And of course, queries can always, you're welcome to ask any queries. I will now like to show you the various aspects, geometrical aspects of the simplex algorithm through this example, and I will trace the corresponding, see this polytope I had discussed with you some time ago when I was showing you the various faces of the polyhedron and so on. So now if you take the same polyhedron, so these are the constraints by adding the slack variables here, and so that means now this polyhedron describes the feasible set for this linear programming problem, and I take the objective function to be x2 plus x3. Okay. And so if I want to continue, I mean now I apply the simplex algorithm to this problem, to this linear programming problem, and here is the first tableau. So this is your top row 0 1 1 0 0 0, and then these are the constraints. So you can see that the starting solution, your basis consists of x4, I mean a4, a5, a6 and a7. This is your identity matrix. So your basic feasible solution reads as 6 6 2 3, but so regular variables x1, x2, x3 are all zeros. So this is your starting point. This extreme point of the polytope is the starting point of your simplex algorithm, right? Then because it's a maximization problem, I take the first positive Cj minus Zj because that will improve the value of the objective function. So then I go for the pivoting, the ratio is minimum here, right, 2 by 1. So we will pivot on this element, and then after the pivoting I show you this is the next tableau. Okay. And now you see that your x2 has come into the basis, it replaced x6. So essentially only out of x1, x2, x3, only x2 has become equal to 2, x1 and x3 are still 0. So the extreme point 0 to 0. So therefore the simplex algorithm from here will go to on this edge of the polytope and come to this extreme point where the value of the objective function now has gone up from 0 to 2. Remember, this number shows you the minus of the objective function value. So we look at this, then again looking at the top row, this is the variable which should become a basic variable, and so you find out the minimum ratio here again is minimum for this. So we pivot on this one. Okay. And once you pivot on this, this tableau shows you the next basic feasible solution, and now you have x2 and x3 both in the basis. X3 is at level 2 and x2 is at level 2. The remaining positive ones are your slack variables. So and the value of the objective function has gone up to 4. So 2 2, that means 0 2 2. 0 2 2 is this feasible point, extreme point, and so that means along this edge. So you see, from here you move on to this edge, come up to this extreme point, because beyond this if you go, the value of the you become infeasible. So, therefore, now from here you proceed along this edge, and the value the extreme point is 0 to 2, and the value of the objective function is 4, right. At this point we were at this extreme point, and the corresponding tableau is here. Then since this is the only positive entry, this is now a candidate for coming into the basis, this column, and we see that the pivot element is this, because ratio here is 1 by 2 and this is 2 by 1. So, this is the minimum ratio. So, that means now x 7 will become a non-basic variable, and x 6 will become a basic variable in its place. So, when after pivoting, this is the tableau we see here, and you see that the top row now has all zeros or minus negative entries. Therefore, we have reached an optimal solution. The corresponding basic feasible solution is right. So, here what is the basic feasible solution? This is given by x 3 and then x 5 and x 2 and x 6, right. But since we are only recording these on the polytope, x 5 and x 6 are slack variables. So, x 3 and x 2, what is x, where x 3 is 3 and x 2 is 3 by 2. So, 0, 3 by 2 and 3, 0, 3 by 2 and 3. So, you move along this edge, and this is the point where you reach, and this is now an optimal solution. Okay. Fine. So, the maximum value obtained is 9 by 2, and this is. So, this is the idea that the simplex algorithm starts from a basic feasible solution, and then it moves along the edges of the polytope of the feasible corresponding to the feasible region and to an extreme point, and then again it changes the direction wherever the value of the objective function will improve. So, see, this is moving to an adjacent extreme point here along this edge. Then for this extreme point, you move along this edge to the next adjacent extreme point, and from here you finally come to the optimal solution, right. So, the movement of the simplex algorithm is always along the edges of the corresponding polytope, and from you move along an edge up to an extreme point, then you go to an adjacent extreme point along another edge, and so on. So, you keep on improving the value till you have reached the optimal solution. Okay. So, I hope this also gives you a feeling about a better feeling about the simplex algorithm. And then see, here we have been also talking about the supporting hyperplane. So, for example, if you look at, see, what was happening here is, if you look at this, this is not a very exact picture, because x 2 x 3 will have a slope of 45. Our objective function is x 2 plus x 3. So, you see this is the maximum value. So, for example, at this thing at point 0 0, if you take the x 2 plus x 3 here, the value was 0. So, you started with the 0 value of the objective function. Then you move parallel to itself, and when you came, okay, not a very good, again a very good drawing, but here. So, here the value of the objective function became 2, right, which is given here, right, and then you move to this extreme point. So, the movement of the objective function is parallel in the direction in which the value is improving or increasing in this case. So, this became 4 here, and then finally, okay, this has to be parallel to this like this, okay, and then it became 4.5, and that was the best value that you can have, right. So, you see, now this becomes, that means x 2 plus x 3 has become a supporting hyperplane to this polytope at the extreme point 0 3 by 2 3, because now the whole of the polytope lies on one side of the, or lies in one of the half spaces made by this given to you by this hyperplane, right, x 2 plus x 3 equal to c, whatever you want to call it. So, that hyperplane. So, in this case, of course, the hyperplane, the supporting hyperplane is equal to 9 by 2, right. So, the half space x 2 plus x 3 less than or equal to 9 by 2. So, this is the half space on this side, because every point of the polytope, every point of the feasible region has value less than 9 by 2 for the objective function. right, and the other half space which will be greater than 9/2 is on this side, but that is all infeasible. So, therefore, the maximum value of the objective function is 9/2. So, I wanted to give you a concept about the supporting hyperplane also, and hopefully through this example you now have a little better insight into the how the simplex algorithm works, and why we need this concept of adjacency, moving along an edge, and then going up to, and that the objective function becomes a supporting hyperplane at the point which is the optimal point, because then that is the best value, and so the whole of the polytope has to lie on one side of the half space when you have the supporting hyperplane equal to the value of maximum value or maximum minimum, the optimum value of the objective function. So, this was my concept. You could have so many other supporting hyperplanes here, right? This is not the only one. So, you can now in fact see that you can you can sort of play around with this objective function till you see that it continues to be a supporting hyperplane for the polytope, and therefore, this point will continue to be a point of maxima for that polytope, right. For example, you can have this as a supporting hyperplane, you can have this as a supporting hyperplane. That means, the constraints itself, this one or this one, will continue to be. So, yeah, you can find out the edges correspondingly. You can have the supporting hyperplane which now meets the polytope in an edge instead of at a point. So, then all these points, infinite number of solutions will be an optimal solution if your supporting hyperplane was meeting this polytope at this edge, and so on. So, you can just have a good feeling about the simplex algorithm. We start looking at special cases and extending the theory of linear programming that I developed so far. So, first of all, let me consider the problems bounded variable linear programming problems. Okay. So, here what happens is that apart from, so the problem actually would be of the kind minimize z equal to C transpose x subject to Ax equal to b, and then we are saying that this is less than or equal to u, where u is a vector of scalars u1, u2, un. So, in other words, we do not want our value of xj to exceed uj, and it is not necessary that all the variables in the problem are bounded. Some may be free to take any non-negative value, but some may be bounded. So, I will develop the algorithm for the case when all variables are bounded, but then you can see that you can modify the pivot rules whenever you have only a partial set of variables bounded, right. Okay, fine. Now, you might say that what is the big deal? We can consider, because we have not been considering these constraints explicitly, remember, because we take care, when we go from one basic feasible solution to another, we make sure that we do not violate the non-negativity constraints. So, that can be taken care of, and but this can be part of this. So, essentially you can rewrite this as Ax equal to b, x plus xs equal to u, where x and xs both are non-negative. So, this constraint set becomes the enlarged constraint set here, okay, and the but then the number of constraints now is m plus n instead of m, right. So, if I have to choose, so now my basis size, that means the basis size will be m plus n by m plus n matrix, m plus 1 this matrix, right. So, just imagine when the problems are small, it may not really matter. You can work with a basis size of m plus n by m plus 1, but if you have, let us say, a few hundred constraints and 1,000 variables, the size is really enormous. It goes up by n. Secondly, the structure of these constraints is very simple, right. The matrix here is identity matrix. X less than or equal to u. So, let us try to exploit this structure and see if we can modify our pivot rules. So, again to take care of these constraints implicitly, not explicitly. If I carry my basis size as m plus n by m plus n, then we are looking at these constraints explicitly. But suppose I can modify my pivot rules such that these constraints can be taken care of implicitly, then I will be very happy to be able to just work with the basis size of m by m matrix, right. So, let us see how can we make sure. Now, so first of all, the idea is that replace a variable at its upper bound by the variable replace a variable x j at its upper bound by the variable x j prime such that x j prime is u j minus x j. So, currently x j is equal to u j, right. So, if I put it and I make the transformation x j prime is u j minus x j. So, when x j is u j, currently this is 0, right, and you also see that 0 less than or equal to x j prime is less than u j, because x j has to be non-negative. So, x j prime cannot exceed u j, right. So, so what is the idea behind this is that I do not want to keep variables which are at their upper bounds. I will declare them as non-basic. This is the way I am going to modify my pivot rule. So, variables which are at their upper bounds, I will try to use this transformation and reduce them to non-basic variables. So, that means instead of x j, I will be carrying in my tableau x j prime, and x j prime currently is 0. It can then become later on positive. It becomes positive, then obviously you by this transformation you know what the value of x j is. So, no problem, right. So, therefore, what we are saying is that we will not maintain, we will try not to maintain basic variables at their upper bounds, but then can I ensure that I can have a basis size of m columns which in which the variables are not at their upper bounds. Can I do that? So, therefore, the idea here is yes. So, let me so claim, my claim is in any, so let me call this problem with this constraint. So, this is, let me call this as 2. In any basic feasible solution of 2, the number of variables not at their upper bound, upper bounds is less than or equal to m. If I can ensure this, then I can always say that I can have a basis for this new bounded variable problem of size m by m. Suppose the number of variables in a basic feasible solution of 2 not at their upper bounds is p. So, I have a basis, that means I have a basis of size m plus n by m plus 1, therefore, the number of basic variables is m plus n. I am saying that suppose the number of basic variables not at their upper bounds is equal to p. So, count the number of variables, count the total number, I should say, count the total number of variables which are positive. positive, right. So, what, how many? See, the variables, when I say basic variables, I am referring to x, remember, because finally I want to work with the basis for this set of constraints. And so, when I talk of variables which are not at their upper bounds, I talk of the variables from the set x. Okay. So, yes, so p of these are not at their upper bounds, right, and a typical constraint here is xj plus xsj is equal to uj, right, a typical constraint, right. So, if xj is not at its upper bound, then xsj has to be positive, because they both must add up to uj. Xj is strictly less than uj, so xsj also has to be something positive, which is equal to uj minus xj. So, then from the upper bound constraints, from the upper bound constraints, constraints corresponding slack variables are also positive, right. Then, since p of them are positive, not at their upper bounds, n minus p of these are zeros, right. From the upper bound constraints, corresponding slack variables are also positive, and these are p numbers, right. Also, xsj is equal to uj for xj equal to 0. So, non-basic values, and these are how many? And these are n minus p in number, right. Therefore, total number of positive variables is equal to p plus n minus p, which is equal to n plus p, and this has to be less than or equal to n plus m, because any basic feasible solution cannot have more than, I am assuming that here rank of A is m, and of course, the rank of this matrix is what? Yes, I should have mentioned it when I said basis size will be m plus 1 by m plus 1 matrix. Why? Because the coefficient matrix is A0 I and I, yes. So, this is, and so therefore, rank A0 I is m plus n, where rank A we are taking as m. So, that is no constraint, because you saw that we can, if there is a redundancy, the algorithm will find it for us. So, anyway, right. So, this is what you have here, and so therefore, the number of positive variables in any basic feasible solution cannot exceed n plus m. So, therefore, this implies that p is less than or equal to m. So, in case p is less than m, we may either have a degenerate, we will have a degenerate basic feasible solution, or we may carry some variables from x at upper bounds. But we can certainly make sure that we do not have more than m positive variables in a basis. So, these variables will correspond to the x variables, not to the, right. So, that shows you that we can work with, we do not have to use these constraints explicitly. We will work with the original tableau and the original basis, but make sure we will keep making the transformations, so that you do not carry too many variables at their upper bounds. Okay, fine. Now, let me just modify the pivot rules for you a bit. So, let us now see how the pivot rules get modified, right. So, let us look at, see, remember, because we do the pivoting, we have multiplied by B inverse. So, for example, here if you look at this constraint, now the transformed constraint looks like x1 or xb1 is equal to, so the transformed is, so let me write the xbr plus summation yrj xj, j belonging to your non basic set. Yeah, let me introduce this notation also, because we say B corresponds to the basis set and non base, and B corresponds non. So, this is equal to your BR bar, which we are also. So, currently all non basic variables are 0. So, your XBR is equal to BR bar, but now we want to introduce, suppose XJ into the basis, and what would be doing? So, in that case it will be XBR plus YRJ XJ is equal to BR bar. So, how does your this thing change? So, when J, when let us say when XJ is becoming basic, a basic variable, right, is becoming a basic variable. So, then the others are all zeros. We are considering how much Xj can become, and we said that Xj therefore will be equal to will be, because XBR will become 0. So, we said this will be BR bar upon YRJ, where YRJ is positive, remember. So, this is how you were computing, because when XJ becomes BR bar upon YRJ, then this is BR, and so XBR becomes 0. So, XBR becomes a non basic variable and XJ becomes a basic variable, and it enters the basis at this level, right. But remember, now we also have this, that Xj has to be less than or equal to Uj. I mean, in case Xj is required to be bounded from above, then we have to take care of this constraint also. So, then we cannot allow Xj to enter at this level if this number is bigger than Uj. So, let us start defining these things now. Theta 1 is your minimum of, remember this is minimum of xbi upon yij, right, where yij was greater than 0. We took this, and that in this particular case came out to be for I equal to r, the ratio was minimum. So, this is theta 1, but then we also have to take care that this theta 1 should not exceed Uj. So, we will have to choose either theta 1 or Uj, but there is another constraint that is coming on, how, at what level Xj can enter the basis. See, what happens is that we were only concerned with the positive Yij's here, but if you have one of the constraints, say for example here in this one, or okay, let us say that suppose I want to, suppose I am entering this column, just for the argument's sake, suppose I was entering this column here, then if you look at now x2, the second basic variable, there is a -1 entry here. So, what happens? Your corresponding constraint is xbs plus ysj, right, ysj into xj, and this is your bs bar. Now, as x, because ysj is less than 0, as xj increases, this value goes up. Ysj into xj, this is becoming negative. So, in order for this equation to be satisfied, your xbs will go up, the value of xbs will go up instead of becoming negative. So far it did not bother us, because we did not take care of, we were not concerned with the entering column having negative entries, because if the value goes up, fine, it stays non-negative, right. So, the value of xbs, because this is an equation, so, or okay, write it this way. So, therefore, this means that xbs is bs bar minus ysj xj. So, ysj is negative, so this whole thing is positive, and therefore, if xj becomes positive, your value of xbs is becoming more than bs bar, right. But then we want this to be less than or equal to ubs, and that is also again if the outgoing variable, if this particular variable for which the corresponding coefficient here is negative for the entering column, if that has an upper bound constraint, we will be bound by that also. We cannot violate this upper bound constraint, right. And so therefore, this implies that what is the restriction on xj? So you will say that minus ysj xj should be less than or equal to ubs minus bs bar, right, which implies that your xj should be less than or equal to ubs minus bs bar upon minus ysj, where this whole thing now is positive. So my inequality does not change. So this, therefore, so now that means, and you will have to do this, you will have to compute this ratio for all those components of yj for which this thing is negative, right. So that means I will define my theta 2 as minimum of ubs minus bs bar upon minus ysj, where ysj is less than 0. So you will choose this theta 2, and therefore we will finally say that the level theta at which, therefore the level theta at which xj can enter the basis is equal to minimum of theta 1, theta 2 and uj. So 3 numbers. That means when it enters the basis, it should not violate its own upper bound constraint, it should not violate another basic variable's upper bound constraint, right. And of course, this is the normal pivot rule. That means if theta, so here what do we do? If theta is equal, so let me write out these 3 cases now, right. Okay. So once we have this computation clear, now I have these 3. So I need, so let me discuss the cases here, and then we can start working on a numerical example. So the pivot rules, the new pivot rules. So first, if theta is theta 1, pivot on YRJ, right, and XBR leaves the basis at 0 level, and XJ enters the basis. Okay, this is your normal pivot. So we will pivot on YRJ and continue with the simplex algorithm. Second, if theta is theta 2, then again we will allow, if theta is theta 2, then we will pivot on YSJ or whatever the number for which, so we will, if theta is theta 2, pivot on the, you want me to write it some way, something, okay, maybe let me say that this minimum is for UBL minus BL bar upon minus YLJ. Okay, this minimum ratio occurs for S equal to L, pivot on minus pivot on, okay. What can happen is, because if I pivot on YSJ, then see, the thing is that YLJ is negative. So we can pivot on this one. Okay, so pivot on YLJ, right? Pivot on YLJ. So therefore, that means AJ will enter the basic set of columns, right? But then, and make the transformation transformation for, because the corresponding variable which is reaching its upper bound, the corresponding basic variable which is reaching its upper bound is xbl. Make the transformation xbl prime is ubl minus xbl, right. So, because xbl would have reached its upper bound, so then this will become 0. The currently x, so in my tableau the variable that I will carry will be x prime bl, which will be at 0 level. So, therefore, it will not be a basic variable, and so my basis will still consist of m positive variables from, or at most m positive variables from among the regular variables, not the, fine. And what will be the third one? If theta is uj, that means uj is the smallest number out of the 3, right, out of these 3. So, uj is the smallest. That means when xj is equal to uj, when uj is the minimum number here, it means that your variable xbr, for which this ratio was minimum, is not becoming 0. This one, because theta 2 is less than, is bigger than uj, that means your corresponding xbl is also not reaching its upper bound. So, they both remain positive and not at their upper bounds. So, therefore, I can only bring, I can pivot on, or I do not need to pivot on aj, because pivoting implies that you are entering it into the basis, but I am not pivoting on aj. I will simply make the transformation xj prime equal to uj minus xj. Do you get the point? So, that I still maintain the same basis, but the value, of course, this thing would have changed. How? So, what if theta is uj, we want to say xbr is not 0 and xbl is not attaining its upper bound. Therefore, make the transformation xj prime is equal to uj minus xj. Yes, I should have made a note here also, that you make that whenever you make this transformation, how do you affect this transformation on the tableau? So, these two cases I should have, here also I should have made that point, that if you pivot on yLj, then because your current basic variable xbl has reached its upper bound, I need to make this transformation. So, how do I do this? See, remember in my this thing, it is ybl times ubl minus xbl, but currently right now in the tableau, say for example, I want to this has reached its upper bound, I want to make the transformation that this should be ubl minus xbl. So, then in this case you see ybl times this, the new ybl times ubl is a constant thing which will go to the right hand side, and this will read as minus because x prime bl. So, the corresponding column here will become minus of the column for xbl, and the ybl times ubl will get transformed here. So, my right hand side will change. So, the objective function, the basic feasible solution has changed, right, because I am making this transformation. I am making this transformation or this transformation in any case. So, in this case we will not be doing any pivoting, we will simply say that the corresponding column, say for example, as I was saying, that if this is to enter the basis, then what will happen is I will take this column, this whole column times uj, write it on the right hand side, right, and then multiply the whole column by a minus sign, because the column for xj prime is now minus times the column for xj. So, this is the change. So, whenever you make these two transformations, you have to, of course, in this case we do the pivoting, then we transform this the current y column times ubl to the right hand side and multiply it by minus sign to maintain it here. And we will also, if you are making this transformation for example, then I will indicate this by a minus sign to say that when you finally get the when you reach the optimal solution, you would have you want to read the solution in terms of the original variables. So, you can then use this transformation and get back to the original basic feasible solution, which is optimal, right. So, that this shows you all the pivot rules. So, I will keep these here and let me show you the steps according to this example. So, what is happening here is the given problem is like this. I have given it in tabular form. So, the upper bound restrictions on the variables are each variable must be less than or equal to 5. If you look at this tableau, the current basic feasible solution, well, this is not, if I want to take this as the basic feasible solution, if I want to take this as the basic feasible solution consisting of x1, x2, x3 as the basic variables, then you see that these two numbers are beyond 5. I can keep this at level 5, but these two numbers are more than 5. So, therefore, I cannot immediately obtain a starting feasible solution to my bounded variable problem, right, since all of have to be. So, therefore, I will now use phase 1, phase 2. So, this is phase 1, phase 2, phase 1 and phase 2. Okay. So, phase 1 and phase 2. So, I add the artificial variables xa1 and xa2, and I add them only to the first two constraints because the third constraint satisfies. So, that means my starting basis is, let me write out here. So, starting feasible solution is for example, here in this case it is 0, I am reading this as 3, so 0 0 5, then 0 0 0 3 4 5 6 7, and then it is 13 and 9. Is it okay with you? x1, x2, x3, x4, x5, x6, x7, xa1, xa2. This is my starting basic feasible solution. Remember, there is no upper bound constraint on the artificial variables. Okay. Fine. Now, in order to have this, so I am carrying the original objective function also, and we will keep the operations, we will do the row operations on this row also. So, here anyway you have to add the these two rows and subtract from the top one. So, add these two rows, that gives you, and subtract. So, -1, -1, this is 0, this is 0, -3, this remains the same, this is -3, 0, 0, and this is -22. Do the same thing here, add this and subtract. So, this gives you 2, this gives you 3, -2, 0, 3, this gives you 0, 0, 3, -4. Right, this I do not have to, in fact I can leave this like this, and then this is also -22. Okay, fine. So, now this is a starting tableau for your phase 1 problem for this bounded variable LPP, right, and look at the first one. So, this is the one to enter the basis. So, here of course, no other entry is negative, so only one positive entry, and see what happens if you pivot on this one, then the entering variable would be at level 13. So, remember what was our rule. So, here you see your theta had to be minimum of theta 1, theta 2, and here it is 5, the upper bound. So, theta 1 is coming out to be how much? 13. The ratio is 13, 13 by 1, which is 13. So, in this case it is coming out to be minimum of 13. Theta 2, there is no theta 2, right. So, it is nil, and this is 5. So, this is 5. Okay. And therefore, what do? We simply make the transformation, as I said here, you simply make this transformation, and what would that mean? It would mean that 5 times this row gets transformed, gets taken to the right hand side, right, and then I multiply this by -9. So, 5 times I do that plus 5. So, this will become plus 5, and that will be minus 17. Then 5 times you subtract, so this becomes 32. Actually this has no meaning right now, right? Then 5 times you do it, this becomes 8, right, and that is it. And then I multiply this by minus sign, because it has to be minus yj of xj, what it has to show here, right. Okay. So now you would, I'll show you one more, and let us just see that quickly. So this is the next negative one. Remember, I don't have to do any calculations here because no pivoting has been done. So when I enter this, this is the only positive entry here, and again the same thing follows, right. So I don't pivot on this one because this is more than 5. So again I'll do the same thing. I'll make the transformation, right. 5 times this whole thing gets transformed to that side. So 5 times when you take it, this will become 12. I will not compute this right now, and then this becomes 4. So you see, this becomes 4, and then you minus, minus, minus. So we will, I will continue with this problem. I will come back, and in the next lecture I will write it again and to show you 2 more iterations, so that I can sort of demonstrate to you all possible pivoting rules that we have to. So once you have modified, you see you can very nicely take care of the upper bound constraints in a implicit way and maintain the same basis size, and so this gives you a little more insight into how the simplex algorithm works. So I will continue with this in the next lecture.